Then you better not copy out of the notes. Okay. In the note, in our notes, you said this one. You have another one that you have to do. Okay. What about 5? Here's 5. Okay, so we've chosen coordinate system, we've chosen intervals. We still haven't fully answered what integral means. What's the other thing? Well, actually we have. We fully answered what integral means. So this looks like integral 0 to r, integral 0 to pi by 2, integral 0 to pi. Now we have to ask the question, what does dm mean? dm means little block of mass. Little block of mass situated at a position inside this hemisphere, parameterized by theta, phi, and r. That's what dm means. Little block of mass. If you know the density where that little block of mass is situated, then the mass is equal to the density times the little volume enclosed by that block. So we have dm is equal to rho, the density, which is a function of r in this case, times dv. And if we were working with a two-dimensional object, instead of a dv, we would have written dA. If we were working with a one-dimensional object, instead of dv, we would have written dx, or dl. Right. So now let's write it again down here. We now have to ask the question, rho of r is CR. What's dv? Hey, who says dr dt to be 5? Who says r dr dt to be 5? Who says r squared dr dt to be 5? Who says r squared sine 5 tan theta dr dt to be 5? Okay. I'm not going to dr because I've got this 1, 5. Right. So that comes from the fact that that is the product of the metric coefficients. The size of a little block of volume is the product of the metric coefficients in an orthogonal coordinate system like this one. The metric coefficient associated with r is 1. The metric coefficient associated with theta is r. The metric coefficient associated with phi is r sine theta. When you take that product, you get r squared sine theta. So this is the product of the metric coefficients in the sense that your little block of volume here between a small change in theta, d theta, and a small change in phi, d phi. Let me draw a bigger picture. uploaded in, I think it was the first week or the second week. And it basically details what happens when you shrink your coordinate systems really, really small. And you can change the slider and you can watch the coordinate system getting closer and closer zoomed in. And as you zoom in, this little piece of volume becomes a cuboid. Right? And the side lengths of that cuboid are dr. And if your d theta is your theta angle, then this side length here will be r d theta. And if your d phi is the change in the phi angle, then this side length over here will be r sine theta d phi. And because these coordinates are orthogonal, and those are the side lengths of the little boxes, in a very formal sense, this all actually holds up. Because these are orthogonal and those are the side lengths of the little boxes, when you want the volume, the little piece of volume, dV, it's very easy to compute. It's simply the product of the side lengths, because this is a little box. So the product of the side lengths is dr times by r d theta times by r sine theta phi. And that's exactly r squared sine theta dr d theta d phi, which is the thing we've written up there. Right, so we've now set up our integral. That's all the hard stuff done. The rest is first doing. The hard stuff was, and it's hard in inverted commas because it's not actually that hard, setting up what coordinate system, what your boundaries are, interpreting correctly what integral means and what dm means. It's going to happen the same way every time, except what will be different is your specific bounds, your specific coordinate system choice. And therefore, obviously, the meaning of dt. Right, so let's evaluate this. That's on the CR cubed. So integral 0 to r, integral 0 to pi by 2. We may as well do the d phi integral. 2 pi 3r cubed sine theta dr. Take the c out, the r integral and the theta integral now need to be formed. It's a bunch of integrations. I'll just write the answer down as soon as someone's completed it and shout it out. The next step would be to do all the other integrals. I'm going to give you guys a 15-minute break. We will start with that break. If you are confident with it, you don't have to stick around. If you have questions, of course, you're welcome to ask them. But this is strictly a tutorial session. We will end when everybody's happy. Which will hopefully be early and not late. Thank you.